All right, so we want to do an example here. So we have a rock face. The angle is 70 degrees. And the first thing we observe is that, okay, this is 70 degrees. And if you look back on what we did last time, this angle is 45 minus phi prime over 2. In other words, when this whole region is soil, when all this is soil, the region that moves with the wall has an angle of 45 minus phi prime over 2. So what we find is that if we have, so in other words, 45 minus phi prime over 2 is here, and we're at 70 degrees, so we can't use, we have to use our free body diagram method. We can't use our active stress method that we have used for other kinds of walls, because this is by definition a small wedge of soil. So it's a 20-foot high wall. This is 4 feet. If you do the math, that's 7.2 feet. And we're taking dry density of the gravel there. It's dry gravel. 100 pounds per cubic foot. The friction angle is 28 degrees. We're going to say that the wall face is very rough. Okay, what is the impact of that? That means that we have full friction generated on this wall face right there. And so we want to find the active force, not the stress. Now, interestingly enough, we can't do stresses now. We're going to end up with forces, because we use forces to evaluate our free body diagram. So we always do equilibrium with forces. We don't do equilibrium with stresses. So, okay, so what we want to do is find the factor of safety against overturning. And so here's our free body diagram. It looks exactly what we had. We had phi prime of 28 degrees. And so it's always going to look like this. We have our W, we have our normal and shear, and then we have to make use of the fact that this is N1, and this is N1 tangent 28 degrees, because our friction angle is 28 degrees. So don't introduce a new variable here. In other words, don't call this F1. Don't do that, because we won't be able to solve the problem. And same thing here. Don't call that F2. Don't do that, because it introduces a new variable. We won't be able to solve our problem. So we have to make use of the fact that there is a relationship between the normal and the shear, and it's through the tangent of the angle. And in this case, since it's really rough, we're going to make use of that. That very rough face means use tangent of phi prime. So that's what that statement means. So we've got our, so we got normal and shear here, N2 and N2 tangent 28 degrees. And so there's our free body diagram. And now what do? We have to take equilibrium. And I always like to, when I draw these out, I always like to put all my angles with respect to the x-axis, because if we do everything with respect to the x-axis, then we end up with sines and cosines in our equations that are easy to keep track of, and we reduce error. So what I want to do is so in other words, I have this force, and I want to write the angle with respect to the x-axis. Well, that's obviously 70 degrees, because there's 70 degrees there. So that one is 70 degrees. And then I need this one. Well, if I draw this, little diagram here, I know that N1 is perpendicular to N1 28 degrees. So in other words, this is a right angle. And if that's a right angle, and this is 70 degrees, that makes that 20 degrees. And so again, the angle with respect to the x-axis, this is 70 degrees, that's 20 degrees with respect to the x-axis, and that's the way I like to do these problems. So I recommend you do the same. This, I don't have to worry about it because they are x and y axes. So we can get the weight of our wedge. We figure out the volume of the wedge. The volume of the wedge is what? 1/2 the base times the height. The dimensions are given. In other words, this is 20 feet. And this is 7.2 feet. And so 1/2 the base times the height gives me the area that we're assuming take 1 foot perpendicular to the paper times 1 foot perpendicular to the paper. So all of this gives me the volume. Volume times the density gives me the weight. The weight of that wedge is 7,200 pounds. So my two unknowns are N1 and N2. My two equations are sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0. We can solve this. So I take the sum of the forces in the x direction equals 0, and so I have to account which, N1 has a component, that has a component in the x direction, that has a component in the x direction. So I only have 3 forces that have components in the x direction. So whenever I do, since I do everything with respect to my x-axis, then when I do the sum of the forces in the x direction, I'm only going to have cosines. So that's what makes it nice. When I do the sum of the forces in the y direction, then all I have sine. So I don't have to think about it. So I've got N1 cosine 20 degrees because that's my angle. N1 tangent 28 degrees, and then it's what? Cosine 70 degrees. So very straightforward for that, and then I have minus N2, no component equals 0. So I can simplify that equation to that. In the sum of the forces of the y direction, it's all sine, so I have N1 sine. Now notice, of course, we have to pay attention to our direction. So notice this goes upward to the right. So that's going to be to the right means positive because I'm taking to the right positive. This one goes upward to the left. Well, left means what? Negative. So I have to use a negative sign there. So make sure you get your signs right. And this obviously is going to the left. So that's going to be negative also. So yes, so where people will make mistakes is with their signs. So make sure that you get the signs correct. And similarly, anything that's going up is going to be positive. So that goes upward to the left, upward, downward. So positive, positive, negative. So make sure your signs are right for that. So I'm going to have positive N1 sine 20 degrees because it's sum of the forces in the y direction, plus N1 tangent 28 sine 70 degrees. So again, we're using our 70 and our 20, minus the W, and then plus the N2 tangent 28 degrees, that one. So I plug everything in, I can simplify that expression down to this. So once I now have 2 equations, 2 unknowns. You can use your calculator, you can do whatever to solve that. I'm not going to solve it for you. But I get that N1 and N2 are these, and then N2 tangent 28 degrees is that. We're primarily interested in these two because that's what go on the free body diagram of the wall. So first I solve the free body diagram of the soil. Then what? I take those forces, I put it on my wall. So there's my wall. Those are the forces we just calculated. And make sure you get the directions correct for these as well, because this is going to go to the right and that's going to go down. And since it's overturning, the wall has the lift off, everything's dry, so I'm taking moments about this point. So in other words, I lift off from there, so I have nothing in the base. And then I simply take my resisting moment, overturning moment. So my overturning moment is going to be the 4385. Now, okay, we're going to take 1/3 from the base. Well, because we usually do that. Now, we don't know this exactly, but this is what we use because, we don't have our stress diagram. When we have our stress diagram, then we can figure out what that is. But, people just generally use 1/3 because that's pretty, fits with what we know about pressure and things like that. It may not be exactly, but that's what people use. So I have, notice, both of these contribute to overturning. That's the way that we address overturning. So in other words, this is the way it's done. So I have that contributes to overturning, going like this, but this one does the reverse. So we have the minus sign there for this force. And the moment arm there is 4. The moment arm here is 6.67 because there it is right there. And so that's my overturn moment. My resisting moment is going to be the W times, it's a rectangular shaped wall, so the moment arm is 2, half of 4. And the result is that we get 1.2 for my factor of safety against overturning. So the concept behind using both of these forces as our overturning forces, is that the concept is that if I'm wrong on this, then I'm going to be wrong on this. And so, sort of compensates for each other rather than putting this as the resisting moment and putting it up here. It just, I don't want to introduce too much uncertainty up here, so I'm keeping all my uncertainty down below there. So that's the philosophy behind it. And again, I should say that, factor of safety is basically a definition. It's not a theory. And so you have to, not theory. We don't have a theory for this. We basically decide what our factor of safety is. And it's just a way to introduce some safety into our designs. And there are different ways to do it, and there are different philosophies behind it, but there's no real theory. So right now, we're sticking with this. And your company or whoever you may work with may have other attitudes about it. All right, I'm going to get started on the next topic, which is, bearing capacity of foundations. And what are we concerned about? So this is the next topic. We're leaving walls, although we're going to use a wall analogy to get to the equation that we're going to develop. But we're not on walls now. We're now concerned about this happening. In other words, I am concerned that if I build a structure that is too heavy, for instance, that this is not a wall, this is a building, okay? Although, because it's not holding up any soil. It's just a building. So this is the original building, and what we're concerned about is that this this building is going to rotate, for instance, about that point here for, just as a way to discuss it, approximately, and it's going to cause a shear failure in the ground, and we got a pile of ground over here, and we get a complete, what we call a bearing capacity failure. Bearing capacity. We also refer to this the stability of the foundation. Stability, bearing capacity means complete failure, and the stability is going to be reflected in the factor of safety that we have against this. This is the classic bearing capacity failure. And okay, so we need to develop an equation for this. I'm going to to look at this. And, okay, so let me go through it. There are different ways to do this, I will just say, because we've talked about this. What in some ways we can simply analyze this circular failure surface and look at the forces along this shear surface and take moments about this point. That's sometimes done, but right now the more common way is to use an equation that I'm going to develop. Slightly different, but there's nothing wrong with doing this analysis if you take everything into account. But the more common way is to do this bearing capacity. And you need to know how to use this equation. I'm going to develop it here. Okay, so this is, said we're getting off walls, but now we're sort of getting back into walls. So let's just say this is my building here, and notice I have a basement. And what I want to do is envision even an imaginary wall here. So, or we can just say there's a wall, a sheet pile wall right there, and that sheet pile wall is the depth that's equal to B. Okay, so the width of my building is B, and this has a depth of B. For the sake of discussion, let's say there's a wall embedded there. A sheet pile wall, so very thin sheet pile wall, for the sake of discussion here. And the concept is this, that if my building is too heavy, what I can do is this wall will move in this direction. So in other words, what we want to know is, when will this wall be pushed over to the side here? So in other words, we know, I'm going to call this is the active region, this is the passive region. And if I look at this, and what I'm going to do is figure out what are the forces on this wall, and when the active is greater than the passive, this wall is going to move, and we have failure. So in other words, we're going to say that then that creates this kind of failure. So we have this weight of this building creates a Q over here, and there's the weight of this soil here creates a Q over here. Now we're going to separate those two Q's. I'm going to call that Q QU, and this Q is Q. So we have these stresses here affect, of course, our active and passive pressure. So I'm going to analyze this wall here, and we're going to do it. So if I take this little diagram, and that's this over here, so I made it bigger. So this is my QU, this is my Q, and so if I were to, I'm going to call this distance H, so I'm going to have, there's my wall, and I'm going to be concerned about the depth 0 and H, and 0 and H on the passive side and on the active side. So those are my depths, and I'm going to figure out, I'm going to have my usual table, sigma V U, sigma V prime, sigma H prime, sigma H. So we're going to assume that we have dry sand here, and we're going to, I'm going to do this with letters. So what's my sigma V at 0? Well, I've got this QU, so that's going to give me my sigma V there. And when I'm at H, what's the stress for that? Well, that's going to be H times gamma D, and then I also have the QU. So this gives me my sigma V's at the top here and then down here. Similarly, on the other side, I can do my passive side. I've got what? Small q, and then q plus h gamma d on the other side of that wall. everything is dry, so my U is 0, so that means my sigma V primes are the same as my sigma V's. My sigma H primes, what are they going to be? Well, what do we know? They're going to be, we multiply, on the active side we multiply times Ka, on the passive side we multiply times Kp. Because this is, dry sand, and that's how we analyze this. And so my sigma H prime, there's no U, so that's the same as my sigma H. So this is, we can calculate out what are the active and passive pressures. And, I have a trapezoid over here, I've got a trapezoid over here, and I can create forces from those. And so, so here's my wall, there's my wall, and here's my passive stress trapezoid, here's my active stress trapezoid, and what do I see? That's Ka times U, so I'm just drawing the wall pressures, like we always have. That's the bottom of the wall. This is my Kp times Q, and that's, the bottom of the wall. That, so in other words, I'm just simply plotting these total horizontal stresses here. And so what we're saying is when the active pressure is greater than the passive pressure, it's going to move. Or, it's going to move just when they're equal. So we'll say that just as the active force, we're saying the active force, sorry, not the active pressure, active force is equal to the passive force, it will just begin to move. And so that's our condition that we're interested in, and we're going to solve for QU. Why are we solving for QU? We're solving for QU because what we want to know is what stress here is going to cause this wall to move. So that's what we're interested in, so we want to develop our equation to find QU. And so what do? My PA has a rectangle and a triangle, so there's my rectangle and my triangle, and the PP also has a rectangle and a triangle, so rectangle and triangle. And so I'm not going to go through this all in detail, but so I now have an equation that looks like this. For the active force, for the passive force, it's that. Then I'm going to set them equal to each other, and I'm going to solve for my QU, and I'm going to define some terms. I don't want to get hung up on the math here, but I'm going to define a term n gamma, and it comes out of this, there it is right there, Kp over Ka minus 1, and nq, which is Kp over Ka, which is there, and this is my pure theory. Okay, so first of all, I'm going to say that I'm not going to focus on these numbers. This is the theory behind it. What people have found is the theory doesn't work that well in practice. So we're going to modify this quite a bit, but I want you to see the theoretical development of the equation and understand where this comes from, because you need to realize that the equation is based on some theory, and then when you have to make decisions on what to use in the equations that I develop, you go back to this theory and you can understand why you're making the decisions you're making. So then if I take these terms and I plug them in, I get this expression right here. So again, we're not going to use this equation, it's pure theory, but we're going to modify it, and this sort of forms the basis of the equation that we're going to use. So if I look at it as 1/2 B gamma D and gamma plus Q and Q. Okay, so like I say, this is going to be the basis for it. And so QU is what? That's the stress due to the weight of the structure that causes failure. So if I know all these terms, so in other words, let's look at this. Do I know Kp and Ka? Well, hopefully. So I know N gamma and NQ. So this is known. this is known because I know the density of my soil. This is B, that's the width of the building. And Q, small q is what? Well, small q, and this is an important part of, you need to know what small q is. Small q is what? Well, it depends on how deep it comes from this, how deep I've embedded my foundation. So, I take the bottom of my basement here, and then this stress, the stress caused by that soil up there, gives me my Q. So that small q with no subscript, just Q, relates to the depth that you embed your foundation. So in theory, we know everything here, and then we've been able to figure out what's building stress, what QU is it that's going to cause failure. So that's the concept, that's the development of the equation in a way, and we're going to modify it quite a bit. And I'm going to note that this works for footing also. So in other words, if I take and I have a footing embedded into the ground, so here's my column load, for instance, and here's my footing embedded into the ground, I also get a Q. And so this analysis also works to see if my column footing will cause a failure. So it's not just for the entire building, it also works for analyzing an individual footing. Now, in this assumption, we're sort of, what we don't see, because this is, active and passive forces, well, so we're sort of assuming a strip footing, what they call a strip footing. So this is a strip footing, like a wall footing, a little bit different from our column footing, so I guess I shouldn't call it a column footing, but in other words, this is a three-dimensional picture of our footing, and it's very long, perpendicular to the paper, and so we call that a strip footing, like a wall footing underneath a wall, for an instance. That comes out of the assumption because, remember, our walls, and this is a wall analysis, and our walls, we always assumed it was very long, perpendicular to the paper. So just a slight thing, we're going to talk about different types of footings. So again, this is our picture. Our footing is embedded into the ground. Oops. And so it's embedded in the ground. We get this Q, this is one thing that confuses students, so don't forget this. Q is the stress due to the soil weight outside the footing. Okay, so you need to know this. Know this, because people forget about it. This is the stress due to the soil weight outside of the footing. So it's this stress out here caused by this soil weight. So you need to know that that's where that Q comes from. Just as we go along, people forget that, and they go, what is Q? And so, okay. Again, we're going to have to figure out our EDS tough. So effective drain slow, total undrained fast. Effective drain slow, total undrained fast. Don't forget about that, because we're going to need to do, when we do our analysis, we're going to have to use that in this evaluation of bearing capacity. So what do we mean? If we have sand or clay drained, then what we're going to find is that we're doing an effective stress analysis, right? So drained, effective drain slow. Effective stress analysis means that Q is an effective stress. That's one other. It's the stress due to the outside weight, but sometimes it's a total stress, sometimes it's an effective stress because of our EDS tough analysis. So sometimes Q is an effective stress. That's when we're doing this. On the other hand, Q can be a total stress, and that's when we're doing total undrained fast, which is what? Clay undrained. So if we're doing a clay undrained, we're going to find that Q is a total stress. It's the total stress due to the weight out here. And then if we're doing EDS, sand or clay drained, then the Q is what? It's an effective stress, which means it's the effective stress due to the weight of the soil out here. So that's going to be, when we use this equation, we have to keep in mind just going to let you know that's going to add some complication in the EDS tough when we're doing either effective stresses or total stresses. It's a big deal. So, okay. And we didn't do it, but if we put in clay drained using C prime and phi prime for our wall analysis, which we didn't, we just had what? We had sand drain, so we only put in a phi prime in our analysis. I'm not going to go through this whole thing again, but if we could redo that whole analysis and we would end up with a different equation, it would be QU is equal to, and it becomes more complicated. And again, this is just theory, but we would get C prime times 2 Kp to the 3 halves plus Ka to the 1 half for that term. Then we have 1 half B gamma B, it's a long story, times this coefficient, and then Q times that coefficient. So we're going to call, I don't want to get hung up on, again, this is theory, so we're not going to use exactly these numbers, but instead what I want to say is we're going to use NC, N gamma, and NQ. We're defining those terms. And in theory, that's what they are. In theory, that's what they are. In theory, that's what that is. But we're not going to use the pure theory when we actually do this. In other words, theory did not work with observed. And so what we're going to do is we're going to get the NC, N gamma, and NQ from tables. I'm going to give you some tables. The other thing that you're going to notice, there's some water in there and all this other stuff. And so this gamma B, when the soil is saturated, is what? Gamma saturated minus gamma W. So notice that that is a gamma B, a buoyant unit weight, rather than a total unit weight or effective, or it's effective, same thing as effective unit weight. So in other words, sometimes this is written gamma prime, because notice it's minus gamma W. It's sort of like a sigma prime. So gamma B, gamma prime. Okay, so this is the equation we get. C prime NC plus 1 half gamma B N gamma plus Q NQ. And I'd like you to memorize that expression. Now, so this is what we're going to be using. This is sort of the basic part of our expression. And so we're going to be using that equation over and over again. So I want you to memorize that. And just to when I say they're obtained from the tables, this is what the table looks like. We're going to have a phi prime, NC, N gamma, NQ. So I have phi prime of 0, I get certain things. Phi prime of 1, I get the, okay. So, except it's going to go, all like 50 degrees or something like that is what the table is going to be. It's not going to stop there. And the other part that you have to, we have to go back, because we're going to be using this a lot, the Ed's tough thing, and we have to keep in mind our failure envelope. So remember, this is my clay undrained failure envelope. For the clay undrained failure envelope, in other words, loading clay fast, we have our intercept, SU, and so when I have my equation here and I see this symbol C prime, the way that we're going to use it is C prime is SU. Okay, we're not going to, why? Because the way this equation works is C prime simply represents the intercept on the failure envelope. On the failure envelope. So if I look at my different failure envelopes, well, there's no intercept there, so I use in that equation 0. There's a C prime intercept there, so I use C prime. There's an SU intercept there, so I use SU as my intercept. So, it's too long to write intercept from the failure envelope there, so nobody does that, but that's what that means. But we always write it as C prime, but you have to remember, do I have this, do I have this, or do I have this? So, and the other part of it is that when we go into the tables, so we said that the tables, what? Look, it's all about phi prime, rather. So it's about phi prime to get all of these values. Well, what does phi prime mean? Phi prime means the angle of the failure envelope. So, again, that is dependent upon what we're looking at. So, what do I use for my phi? If this, well, my angle is 0, so I use phi prime equals 0 to get my NC, N gamma, and Q. Here, my phi prime is phi prime to get my NC, N gamma, and NQ. And so that's the easy one, and it's easy down here. Phi prime is phi prime to get my NC, N gamma, and Q. So we just have to remember for this one, the main thing is that I recognize that I use my phi prime of 0 under this clay undrained situation to get my my N values, which are not N values, we call them bearing capacity factors. So these three are called bearing capacity factors, NC, N gamma, and Q. Okay, I'm going to stop here.